Hello everyone, welcome back on the course of higher surveying, and we are in module 6 on photogrammetry. In the last lecture of this module, we have discussed about a lot of scattered information which was very introductory in nature, and then we realized that what are the types of platforms, what are the types of photographs, and many terms like basic terms, aperture stop, focal length, focal plane, and so on. Now in this lecture, or rather from this lecture, we are going to be very specific for a particular aspects of photogrammetry. Okay, so today we are going to talk about vertical photogrammetry. So this is our lecture 2 on vertical photogrammetry. If you remember, or if you can recall the last lecture, we talked about different types of photographs. First was vertical photograph, tilted photograph, and oblique photograph. And there in the vertical photograph, we said that the nadir line is coinciding with the optical axis of camera. So that was our idea to categorize the photographs into 3 categories. So if optical axis matches with the nadir line or the gravity line or the plumb line of camera, then we say that it is a vertical photograph. If it is tilted, in a sense optical axis is tilted within 3 degrees from the nadir line, we say it tilted photograph. And if it is more than 3 degree, we say that oblique photograph. Well, we will not go into the bifurcation further, but we will try to understand the small nitty-gritties of these aspects today. Also, we are going to understand technically what does it mean and how we can make the map using these photographs, especially the vertical photograph and tilted photograph, because tilted photograph is a kind of tilt that is introduced unintentionally, unknowingly, but we know what is a tilt. So tilted photograph and vertical photographs are treated in this lecture. So let us go ahead. So these are the books again. Well, first 3 books are again still sufficient for this lecture. Okay, so what is the field of view? If you look carefully again, in case of vertical photogrammetry, where we say that a camera is mounted in an aircraft, not in the other platforms. For example, terrestrial platform, we have then low altitude platform, we have aerial platform, and we have satellite platform. So in this case of vertical photogrammetry, we are saying that camera is mounted in aircraft or helicopter. That means we are doing aerial photogrammetry. Like this is my flying direction. Okay, so this is what we call a pixel, which is shown by a black color over there. Right, this is your pixel on the ground, not on the sensor. Generally on the sensor we call one unit as pixel, but when it comes to the ground, that means it acquires some area on the ground surface, then we call it the size of pixel as ground sampling distance, or GSD. Right. Secondly, I am now talking about the digital cameras because they are the only popular one now. All the film based cameras are more or less obsolete. So we are going to talk about now digital camera in the photogrammetry. So now we have a digital aerial camera mounted in aircraft, and that is acquiring one scene, and this scene is explained by these pixels. So in one scene it is acquiring, it is a frame camera, so it is making one exposure and acquiring this scene. So in this scene I can say that so many pixels are there, and one pixel size on the ground is called GSD, ground sampling distance. Okay. So now this angle, which is along the direction of flight, it is called theta y. I am putting it by a symbol, and this angle is nothing but the field of view along track, and that is called the flying direction. Okay. Similarly, we have another field of view which is called field of view across the track or across the flying direction. Okay. Now if you look at again the one GSD, this pixel on the ground is going to subscribe some angle on the camera or on the sensor, right. So let us see, this is the angle there. So each of the pixel is subscribing some angle on the sensor surface or the camera perspective center. We will look into these further terms, so just wait for a few minutes. So yeah, now the angle subscribed by the one GSD or one pixel on ground, it's called instantaneous field of view. Okay, if I write it like this, instantaneous field of view or I of OV. So, this is my I of OV. Okay. So, this distance which is across the flying direction is called the swath or swath width. Both names are popular, we call it swath or swath width, both are the same. Okay. So, now you can see that the instantaneous field of view in x direction can be calculated by the FOV in x direction, or what we have written theta x divided by number of pixels in x direction. All right, fine. So, like this. Okay. So, I can write here, let us say the number of pixels is equal to nx. So, then I can write that on this side the IFOV x equals to theta x divided by nx. All right. So, I can say here that these number of pixels are equal to, from here to here, they are nx number. So, I can find out this. Similarly, if number of pixels here from 1 to, let us say this number is ny. So, I can write I of OV y is equal to theta y or the FOV in y direction divided by number of pixels in y direction. One should note here that in general, since the pixel size on the sensor is same for x and y direction, that means we have square size of the pixel. That is why the FOV in x direction and number of pixels in certain direction x or y, they are basically decided or designed according to this criteria. All right. So, that we will have the square size of the pixel on sensor, as well as that square size of the pixel on sensor should create a square size of grid or square size of box or GSD or ground sampling distance on the surface of earth. All right. Let us come to the vertical photograph now. In the previous slide, I assumed that camera optical axis and the Nadir line or the gravity line are matching. Okay, let us look into what does it mean. So, let us say there is a terrain where this distance is nothing but a swath, for example. Okay, so let us say this is my camera assembly. Okay, so this is my flying height h, right. So, this is my negative image plane and this is my exposure center where all the rays from the terrain are going to meet and they are going to again diverge towards the image plane. So, this is the optical axis here shown here, fine. So, this is the focal length, as you know already from last lecture, right. So, this is the way all the rays are converging to the perspective center and again they are diverging to the image plane. So, and they are creating an impression on the sensor or the image plane, or we can say negative plane. Now, since negative and positives are no more a valid term, but still in the books these things are given and still we are going to use these in order to distinguish between a negative plane, that is a sensor plane, or the image plane which is a positive plane which we really see, because as we know that negative plane image is an inverted image and that we cannot work with, and that is why we need a positive image. So, this is my positive image here, right, shown by here, and which is also located at a distance called focal length from perspective center. So, that is the overall idea you have and you should develop this idea first. That means, what is the mechanism of data acquisition for a given one exposure of the frame camera. Okay. So, that is my swath as I already told. Well, what about this distance? This is also called the swath, but swath along the flight direction. So, this is the swath, what we call swath is my swath across the flight direction, and generally we do not write across the flight direction, we rather only write the swath. So, this is called swath, the whole term. So, whenever you want to specify this swath which is along direction, you have to specify like that. Okay. So, now I can write that swath is equal to 2h tangent of theta x by 2, because the across the flight we have theta x is my field of view, total field of view. It is very simple relationship, you can find out yourself also. Okay, let us look deeply, more categorically into the vertical photograph mechanism. So, that is my negative image plane, what I call, and this is why this is my perspective center or exposure station, this point. Okay. So, this point, yeah, originally when we used to have the negative planes and negative images, so once we develop those images, then we have 4 marks. So, these 4 marks were called the fiducial marks, which are at the center of the edges of an rectangular image. So, if then connect them by straight lines, they will intersect at point, and that point is called the fiducial center of the image. That means, if I take 4 fiducial marks, I should write all fiducial marks now. So, once I intersect, if I draw the line through the fiducial marks which are opposite to each other, then I will find an intersection point, and that intersection point will be called fiducial center. Okay. Let us go ahead. So, this is my optical axis, right, and we can see here that fiducial mark and optical axis are not meeting at a common point. Why? Because I am assuming that although it is vertical photograph, but there is some random error in the optical axis, and as a result it is not matching with the fiducial center of the photograph. Yes, what about the random error? If you can recall the concepts of the adjustment computations and our error accuracy, it is an inevitable error. It is random, it is out of beyond my control, or I cannot measure it. I do not know its true value. So, still I am taking a chance and I am putting it slightly away to show that, right. So, this is the point where the negative image plane and the optical axis intersects. This point is called principal point, or it is also written sometimes PP. Well, next is, this is the principal distance, that is the distance between the principal point and the exposure station along the optical axis, and that is called the focal length. Fine, you agree with that? Okay. Now, that is my positive image plane which is just shown here. Yeah, fine. This is the again fiducial center mark, center of positive image or photograph, or I can say there is a fiducial center on the negative plane. Same way, impression of that or the same point if I am marking on the photograph by taking the intersection of fiducial marks, then I will get center of the positive image. Then if I extend the optical axis down towards the positive image, it will interact somewhere here. So, this is my principal point on the positive image plane. Okay. So, let us draw some axis x and y, like x axis and y axis to the photograph, so that I can refer any point in the positive image. Like this is the gravity direction. So, now you can see even the fiducial center of the image is not matching with the nadir point. The nadir point small n in the image is a reflection, or is it the image of the real nadir point on the ground, where gravity direction is going to intersect with the ground. Fine. So, that is a kind of mechanism of the vertical photograph, that is we should understand before we go ahead. So, if you have any doubt, just go through the video again to understand these things. Or one thing I would like to say here, so we have realized by this photograph that my optical axis need not to match with the gravity direction, or there is a random error, that is why we are not matching them, and we know it that there is a random error, although we cannot measure it. Secondly, optical axis itself is not matching with the fiducial center of the negative image, right, but still optical axis, gravity line or any other line, they are passing through the exposure center, right, and exposure center is the place or the point where all the rays from the object are coming and they are converging, and then again they are diverging towards the image plane. So, that is the idea here. Okay. So, this point let us say is the projection of nadir point in positive image. So now you can understand how are they different. So let us talk about the vertical photograph and the scale. That means if you remember the scale of the map from the basic surveying, what is the scale? Scale we define as the distance on the map to the corresponding distance on the ground surface. So same concept is there, but now we are going to do for the photograph. Moreover, we are taking the vertical photograph. Third thing, we are assuming that our optical axis and the nadir line or the gravity line, they are matching exactly with each other. That means we are talking about the theoretical derivations. And there is no harm in doing this derivation because it is going to simplify many aspects of my work and understanding. And that is the reason we assume that there is no distortion in the optical axis or the principal point. So principal point is matching with the fiducial center of the image. So let us see there is a datum. Then we have a point A here called A0. Then we have optical center O here, and this is the positive image, and the small a0 is the image of point capital A0 in my photograph. So let us say this is the K is nothing but the optical axis OK. This is my optical axis here, and that is also matching with the gravity line or the plumb line passing through the exposure center O. So this is my exposure center or perspective center. Okay, so now this is the scale, the distance on the photograph to the distance on the ground. That means if I take 2 points on the photograph, then if I take the same points on the ground, and if I calculate 2 distances, and if I take the ratio of the 2 distances like this will be equal to the scale of the photograph, because I am assuming now that I am going to use my photograph to make the map. So I am going to find out what is the scale of my photograph, so that I can measure distances directly from the photograph. Okay, so that is the idea Ka0. If you look at here, Ka0, this distance, this is divided by Ka0, that is, it should be K0A0 here. So now let us develop some simple mathematics of similar triangles. First is this triangle and second is this triangle. Okay, so the bigger triangle is there, shown by blue color now, okay, and the second one is the small triangle shown by the red color now, right. Okay, so what about the S? It is nothing but OK divided by OK0. Why? Because that is my OK distance here, which is equal to focal length, you can see here, and this is equal to the flying height of H. Why? Because I can say that this distance, which is this, and this distance, if I take the ratio of 2 like this, they are equal to this distance focal length and this flying height, this distance, and that is written here. So my scale of a vertical photograph is equal to the ratio of focal length to the flying height. Okay, so now we give S is equal to F by H. Okay, so what again, that scale of a vertical photograph, once again we are talking about, let us say there is a ground surface like this and there is a datum like this. That means I am measuring my flying height with respect to the datum. So if you see that there is a point on the ground which is A, and on the datum its projection is A0. So if you look at here, fine, so this is my point photograph is there, this is the A point, that is image of this point is this, okay. Similarly, this is my optical axis that just I drawn, and then if I say here that K point is my principal point, or capital K point is the projection of the principal point on ground, and K0 is the projection of principal point on the datum. So datum has certainly some height, as you remember from basic surveying we measure the height from datum. So now I am saying that there is a plane datum and I am measuring the height of point A. So this is the height HA of point A with respect to datum. and as a result of that, what happens in the scale? Just see now. So, I have the flying height h, and if you see here, this height above the ground of point A, it is h minus h a, right? Fine, let us go ahead again. So, my distance now, the k a is this distance, and distance on ground is k a, which is from this point to this point, this distance, right. So, again I will use the similar triangles, but there is small difference in the scale expression now, because of the point A is above the datum with the height h a. So, let us look what is happening here. So, again use similar triangles, two triangles I am using. So, that means one is this triangle OKA, you can see O, K and A. So, I can say the scale with the same expression f by h. Now, I am writing this ratio, this f here, which is nothing but this distance from here to here, and then this distance, which is from the exposure center to the point. So, this is the scale I get at point A. So, I can write in general, for any point of having h elevation, I will have the scale, and that is what we call the point scale, the scale at that particular point. So, I hope you get the idea what is this. So, at point A, I have this scale, A on ground, right. So, because h a is above the datum, so you will get better scale or higher scale on the photo. Similarly, what if the point A is below the datum? At that case, what will happen if I write in general a simple formula, that is h is equal to f upon h minus of h, because this height h is measured below the datum, that is why I am putting minus h, and as a result I will get h plus h. So, if a point is below datum, I will get inferior scale or smaller scale, but if a point is above the datum, I will get the better scale or superior scale. Remember that we always measure the flying height with respect to the datum, because on the ground we do not know anything before going to the field, but from the map I know where is my datum, and that is the reason we always take the flying height with respect to the datum. So, with respect to datum, when we take the height h, then in that case this scale is calculated. Okay, let us go ahead. So, again we talk about the scale of the photograph. Here I am showing the 2 points, you can see here these triangles. So, at point A I have this scale, and at point B I have this scale. Got it? I hope you are very much familiar now with the scale idea. Okay, so let me define some different type of scale. First of all, I define a datum scale, which means scale that is available at datum. That means if a point A is lying on the datum, that will be this scale here, and we call it SD, that is scale at datum. Okay, what if the point lies above the datum? As we know, this is going to be the scale, and that is called the point scale, because this varies from point to point. Okay, now as we know that terrain is always varying like this, or maybe some other differentiation is there or other variation is there in the terrain. Because of that, we will have different elevation at each point. So, each point will have a different elevation, each point will have a different scale. But as you know that map is always having a uniform scale. So, I need to derive some uniform scale. So, what will I do? I will derive a term called average scale, where I will take the average value of the terrain elevation, that means averaging, maybe I am averaging all the points, and then I am taking the average elevation, and so I am defining the average scale. Remember that average scale is not the final scale or is not an absolute scale. Definitely from each point scale will vary, but still in order to make a map, I need to define an average scale, and that is why I am taking average elevation HAV from most of the points. So, this is a preferable scale when the variations on the ground surface, that means the height variation of different points on the ground surface, are in same order, right, and accordingly it will decide the scale. So, if the variations are very high, for example 200 meters, in that case this average scale will not carry any meaning. Why? Because one point definitely having very high scale, which is on the top of a hill, and there is another point which is on the ground surface, which is having very low scale. So, if I take the average, this average scale is not going to represent the real ground, and that will give me the map created by such average scale will give me lot of errors. So, we should be very careful while we use any scale. Okay. Let us go ahead now. So, let us talk about some kind of displacement that happens or that are evident on the vertical photographs. So, first is a relief displacement. So, let us see there is a datum like this, datum surface is this way, fine, and from datum surface if I measure the height HA and HB for 2 points A and B on the terrain. So, I will have these points HA and HB. So, they are the elevation from the datum. Now, let us see the B0 is this point here, and similarly I have A0 which is this point. Okay. So, let us say there is an image and there is an exposure station, and so this is the optical axis which is piercing here the datum here at K0, and so I have principal point K here, and the impression or the point principal point, if it is touching the ground surface, if I extend the optical axis or the nadir line. So, in the gravity direction this is this point here, fine. Okay. So, the height of the point K with respect to datum is HK. Now, the point A here, this point, it is imaged here, and that point I call A. Similarly, for point B, I call point B here, fine. Now, what if I make the image of point A0 which is at datum, may not be visible to me, but still it will create an impression of A0 here. So, this is the point this point is my A0. Similarly, this point is my B0. Let me mark it B0, yeah. Okay. So, you can see that because of the height of the point A or point B above the datum, you are getting the image of the point B at slightly shifted. That means, the point B if here at the B0, then it should create an image here, fine, as you can see, but the point B is at height HB above the datum. So, it is creating image at B, right. So, as a result I can see that the image of point B is shifted from B0 to B because of the height of the B or height of the location B with respect to datum, and I am still measuring my flying height above the datum, right. And as a result now you can see that each and every point which is above the datum will shift in the photograph from its bottom location. So, you can see that if there is a building which is at ground surface, so its point on the ground surface will have different image than the top of the building on the image, and that is what we call the relief or the relief displacement. Or assume that building, and this building does not have any height, that means which is ground only, right. This point will be imaged somewhere in the photograph, and this point will be displaced because of this height, let us say h. So, that is the idea, and this displacement in the image of the point because of its height above the datum, it is called relief displacement. What is relief? Relief is some height, and because of the height, image of that point is displaced from its bottom, let us say like that. So, this is my flying height h. So, line K B0B, I can say here. So, this is my relief displacement here, which is written here. Similarly, I have relief displacement BB0 for point B, this is this distance. So, now let us try to understand what is the concept again. So, let us say there is a tower, and as a result I want to do some mathematical derivation. So, this is the one triangle. So, I can say that point R0, it is showing the location of A0 here, right. Let us look into this thing. So, this distance is R, and again this distance for point A0, this is this point A0 and this is point is A here. Now, I can see R and R0 are the two distances, radial distances from the principal point. So, now if I draw the two similar triangles, so you can see here from the bottom also this distance is R and this distance also R, right. So, now I want to derive the mathematically what is the meaning of relief displacement, or I want to derive some mathematical terms so that I can connect the height h of the building with respect to the relief displacement on the image. Let us look into this thing. Okay. So, this is R0 and R as marked here, fine. So, this distance is, I can say here R equal to K0 A0. So, this is my K0 here and this is my A0 here, which is bottom of the building or the tower here. So, K0 A0 is my radial distance R as shown in the previous slide in a better way. So, now if I take this two triangle, this F, if I take the ratio of F to the flying height h minus h, this ratio to this is equal to the, if you see here, it will be equal to R by R. R is nothing but K, I can write small k to the A divided by K0 A0, right, and you can see this relationship is very true. Okay. So, now I can write that radial distance R of point A from the principal point is equal to this much, R f into h minus h. You see the focal length I know the flying height. Let us say that I know the height of the point A above the datum also, or above the ground surface also, right. So, above the ground surface means I am fixing my datum at certain point on the ground surface, that is the meaning here, right. Similarly, I can write from other triangle this relationship f upon h, that means the ratio of focal length to the complete height h, which is this height, okay, equal to R0. R0 is nothing but, I can write here K A0 divided by K0 A0, okay, and as a result I can write from this equation that R0 is equal to Rf by h. Now, what is the displacement? Let us look into this thing. So, this is the displacement of image R0 to R. So, I can say that the displacement of the image point because of its height above the datum is d, and which is given by this one, right. We are just doing some simple subtraction. Okay. So, I can bring this thing here from there. Okay. Let me write this thing by just transferring. I can write this expression. Further, I can say what is the value of R here. So, R is nothing but, I can write like this, okay, and then I can also write equal to this one. Why? Because from there I am writing this term. I hope you agree with that. And similarly, from this term I am writing this term, and from here, so yeah, I am writing this term. So, that is equal to the R. Fine. And as a result, if I replace this thing here in the R from here, I can find out this distance, this expression, where d is equal to given by R into h minus h by f into this thing, finally this expression. Okay. Now, if you can imagine that you can measure R on the image, because you know if this is a tower, so this is the bottom of the tower here and this is the top of the tower. So, I can, once we see the image of the tower in the photograph, so this is a point A and A0. So, this is my R here from here to here, and I can measure this thing. Similarly, I know flying height and assume that I know the height of the point, or that is height of the tower, this, what is tower height above the ground surface. I can find out what should be the replacement of, or what is the shift in the image of the point. So, similarly, I can also write this thing you can derive this thing. Instead of putting this expression here in this equation, if you put this expression in this r, you will get this expression. And so that is the idea here. So that means even you measure the r0, which is nothing but the distance of the image point a0 from the principal point, and a0 is nothing but the image of the bottom of the tower or bottom of a building and anything, fine. So still you can measure what should be the displacement of the image of a point A because of its height above it, and that is what we call relief displacement on a vertical photograph. So if you look at the characteristics, you can see that relief displacement increases with the increase in the distance from principal point. The principal point is nothing but small k on the image. The relief displacement decreases with the increase in the flying height, because if you just see back, this is the expression we have h upon h minus h here. So if you can see here that relief displacement of a point on the ground which is above datum is positive, as I already explained, and below datum is negative, and relief displacement decreases with the increase in the flying height. So if I increase the flying height here, the relief displacement will be lower, right? And that is the key. If you don't want a relief displacement, so better to increase the flying height. So what will happen in that mission? All the buildings will appear almost very, very small. But in other sense, relief displacement also give me some sense of height. So choice is yours, whether you want to suppress the heights or whether you want to increase the heights represented in the photo. Choice is yours. Secondly, if you can imagine now satellite at the height of 750 kilometers. So if the aerial photograph, we define the relief displacement with this height h. In case of satellite, I will put this h is equal to 750 kilometers or 900 kilometers, whatever the height, and as a result you will not find any relief displacement in case of satellite images, and that is best source. That means the satellite images are best source for the planning metric mapping. That means I want to do the XY mapping, not the 3D mapping, right? And that's the idea here. Why do we prefer the aerial photography or aerial photogrammetry compared to the satellite photogrammetry? The satellite photogrammetry will give me minimum vertical exaggeration or the vertical distance measurement possible, and as a result I cannot create a reliable 3D information maps using satellite photogrammetry. But in case of aerial photogrammetry, I will have relief displacement, and by some way if I measure the height of the buildings or height of the terrain points with respect to datum, I can prepare the 3D map. Okay. The height of an object, let us look into this, can be determined by relief displacement, and let us see how. Okay. So height of an object, here you see, let us say mean sea level or my datum, selected datum, and I want to find out height of this point A, this height h. So let us say this is my image, I am making it again without going into detail because we have already seen this thing. So this is the D, right? So I can write h is equal to the height of the tower or building. I will measure this D, which is nothing but this D distance. Okay, I know the flying height and I know the R, that is the image of the top of the point from the principal point here, K. So this distance if I measure, this is my R, I can find out, or I can also find out if I measure R0, nothing but this is my R0 from here to here, small distance, or I can write like this, this is my R0 here. So I can still find out from this formula what is the height of the point above the ground surface, and that is the advantage the vertical photogrammetry, that's the advantage vertical photogrammetry, especially aerial photogrammetry gives me compared to the satellite photogrammetry. Now let us take the tilted photographs. What is the meaning of tilted photograph? As I told that when we say that there is a vertical photograph, which means the gravity line is matching with the optical axis. Theoretically it is correct, no problem. But we again say that because of some random errors, we can assume that optical axis is not vertical or it is not matching with the gravity direction like this. Rather it is slightly shifted in the photograph and it creates a principal point away from the fiducial center. Now imagine that there is a tilt, that means optical axis is tilted with respect to the nadir or the gravity direction. What's the meaning here? Again, it is unintentional tilt, but still there is a tilt and I know it there is a tilt. That means it is no more a random error. It is a kind of systematic error that I know. So, tilted photograph, I am saying I know what is the tilt, although it is unintentional, it is undesired. I am not doing it deliberately, it is happening, but still I measure what is the amount of tilt. I know it beforehand. So, let us look into that how my scale is going to change, because we have seen that if because of the vertical photograph where optical axis and the plumb line are exactly matching, in that case what is the vertical scale of the vertical photograph? Now, we will see what is the scale of the tilted photograph. So, let us see there is image plane, this positive image plane. So, this is the point N, which is the nadir point on the image. I can say here, right. So, this is my optical axis and it is creating principal point K. So, this line which joins the small n to K, it is called principal line. This is angle is tilt, fine. And if I draw a horizontal line in a horizontal plane like this, then you can understand that this is angle is tilt here, T. They are same, this T and this T, but they are in different planes, they are appearing different in this animation. So, I am showing that this is my tilt here with the respect to horizontal, and there I am showing this is the tilt here between this is my nadir line or the plumb line, and this is the optical axis. I am showing like this. So, this is my optical axis by finger and the pen is showing the plumb line. So, this is my tilt angle here. You can see here tilt angle. So, that is shown in the animation. Now, if I bisect the tilt angle by a line as shown in the animation, it will intersect at point I, and this point I is called the isocenter of the image. So, now we are trying to find out I also, right, and there is a reason for that, we will see how. So, this isocenter is there. Now, we have understood what is a tilted photograph. So, in the books you will find this kind of photograph, right, where this is my end point here, this is end point and this is my K point, and so this is the tilt angle, total tilt angle is this. So, as a result this point is my isocenter, which is the bisector, or if I bisect that tilt angle, I will get the point I isocenter on the image. Now, let us measure the scale of the tilted photograph. So, let us say this is a point A on the terrain, so there is a datum. So, point A has height HA, okay. So, let us say there is an image. So, there is a point N and there is a point A here which is imaged. Now, this is my focal length f, because this is my optical axis, okay. So, this point line joining N, let us say this is line N here, point N here and the point K here. So, this is my principal line, okay. So, if I take point A and draw the perpendicular to the principal line, I will get my point M, and similarly if I draw the line from point M to the vertical line or the gravity line, I will get M dash, right. Because of the tilt, that means my photograph is not like that and like this, and I know that my nadir point which was like this now has shifted from here to here. It is passing like that. So, optical axis is like that, fine. So, this is my focal length, this is a nadir line here, right. So, this kind of arrangement is there, and as a result what happens is, because this is focal length which is perpendicular to the image, tilted image, and now this one. So, I know that this distance which is little smaller than this distance, right, has to be taken for the scale calculation. So, let us see this distance if I take here up to M dash, then this distance divided by the flying height, which is nothing but this distance, this is my scale in case of tilted photograph, okay. So, let us draw an triangle which is in the horizon plane. So, now we are also drawing the same triangle in the ground surface also, which is shown by NMA. Okay. So, this is my flying height h, this is the point h minus HA, this triangle, that means O M dash A in the image, and this triangle capital O, capital N and capital A, they are similar triangles. So, I can say M dash A divided by NA is my scale of the tilted photograph and not the vertical photograph. I am saying this M dash A, and as I told that M dash A is not measured along the nadir line here, but this distance is from this point to this horizontal plane, like this distance, fine. So, this distance I am trying to measure, and I am showing the ratio of this distance to the ratio of flying height, which is h minus HA, is going to be the scale for point A, if point A is on the tilted photograph. Okay. So, now M dash A divided by NA, it is nothing but O M dash, again I am taking the same ratio, right, by ON. So, ON is nothing but this distance, which is nothing but equal to, this is my ON distance, h minus HA. Now, let us calculate the OM dash, which is slightly complicated because of its involved mathematics. So, let us do this thing. Now, OM dash, it is nothing but OM dash, I am writing it ON, which is ON, you can see, minus M dash N, right. You can see this thing from this simple photograph. So, ON is equal to the f sec t, where t is my tilt angle, and M dash N is equal to Mn into sin t. So, you can use this triangle shown here. Okay. Fine. Let us go ahead. So, now coming to the ON, as I already told, ON is equal to h minus HA. So, I can write that SH, the scale of the tilted photograph, is equal to this ratio to this ratio, or this distance to this distance. So, this is my this distance and this is my this distance here. So, this is the scale of my tilted photograph. Still there is something to say here. Let us wait. Okay. Again, now what happens is, if you go back to the photograph here, we have assumed that we are measuring these distances along the principal line. In fact, on a photograph, we do not measure anything on the principal line. It is just a concept. We measure with respect to our fiducial center only and the axes which are parallel to the edges of the photograph. And as a result, let us draw this thing here. Let us say point A, and that is NK and M. So, this angle is theta, right. So, this is y dash and now x dash axis. So, what I am doing, I am saying that I am measuring this point A here in the image coordinate system, what I call xy, but I know that I should measure this in the x dash y dash system, which is at angle theta, because I know if this is the principal line shown like this, its angle is theta here with respect to the y axis. So, I can write here that these are the desired coordinates, that means distance from A to M here, right, and these distances are required from A to this line. So, I can say this is my y dash and I can say it is x dash, because x dash is measured along this axis x dash like there, and y dash is measured along the y dash axis here, and this is my principal line if you see carefully. Fine. So, now I have to correlate my image measurement, which is x and y. So, what is my x and y? This is my y for this point and this is my x, right, for same point A, and this is my x dash from here to here and this is my y dash. Okay. So, let us write x dash equal to, I can write by simple transformation, as you already know beforehand from the module 2. Similarly, I can write y dash equal to this much plus f of this term will also come, because plane is tilted, it is not in horizon plane, image plane is tilted plane here. Okay. So, now you can see that in the last slide if you go, and there was a term called Mn, which is nothing but equal to the y dash. Here if you see mn, this distance was there, and which is nothing but y dash. So, I am putting the y dash here instead of mn, and my y dash is given by this. Now, you can measure the scale on the tilted photograph also. Try it yourself, try to do some experiments with your mobile camera. Put it like that, create some object, try to put some kind of tilted image like this and capture it and try to calculate the tilted photograph scale. Also, try to calculate something related to the relief distortion. That means, if there is a point like this, let us say there is some building like this you have. So, put it on your table like this, you can put it, and then try to acquire the photograph like this and try to see how this point, the bottom of the pen and the top of the point has shifted in the image. Because of the height of the pen, you will find out that this point has shifted in the image outwardly from the principal point. Fine, that is the idea here. Try to do these experiments yourself. This is very simple because you have the mobile camera with you. Assume that mobile camera is mounted in an aircraft and your hand is an aircraft. So, now you are acquiring the photo of a certain terrain where this is a building. So, now if you take the photograph in which this is appearing, so you will find out the bottom and the top of the pen are appearing at different positions, and the difference from the center, which is I am assuming that center of the photograph is the principal point. So, if you take the radial distance from the center to the bottom image or the image of the bottom point and the image of the top point on the photograph, you will find out they are lying in a one line approximately, assuming that there are no distortions in the optical axis and the gravity line. So, radially they are outward. Similarly, you can do another experiment. Assume that this point building is like that, or there is some valley where you are saying that okay, this is a top point. No, this is your bottom point and this is a point below the bottom or below the datum. So, you can find out what is the negative relief or the effect of the negative elevation on the relief. You will find out that it is inward in the radial line. So, that is the idea here about the relief displacement. Similarly, we just talked about the scale of the tilted photograph. Now, if we go ahead, right. So, length of a line. So, let us measure the length of a line on a tilted photograph. So, what does it mean? We are trying to measure the length of the line on the ground surface using tilted photograph. That means, I am going to measure the measurement on the tilted photograph of the image points. I know the scale of tilted photograph that I already determined, right. So, then I am finding out what could be the distance between the 2 points which I do not want to measure in the field, rather I am measuring from the photograph itself. Let us look into this thing. So, this is my tilted photograph and I can see the red triangle here shown by red color. M dash A is my in the horizontal plane and tilted photograph is this. So, I have a plane like this and there is a tilted photograph like this. So, in this horizontal plane I am defining my triangle M dash M A as we did it in the previous slide also. Okay. So, let us see SH is equal to AM by AM. You can see now the we are defining the scale of the tilted photograph here, right. So, AM is this distance in the red triangle. Now, AM is equal to x dash perpendicular to the principal line, which is nothing but y dash line in the photograph. Okay. So, I can write here that AM, which is x coordinate here in this x and y axis system, this is my y axis. So, AM is nothing but this measurement, this point to this point, this measurement, capital X, I am writing it here, and that is x dash divided by SH and given by this way. You can refer the previous slide for the final expression. Okay. Now, again I can write further in order to find out what is the y distance, but now this time I am using M dash M, which is measured parallel to the principal line, right. So, I can write this thing here similarly, M dash M is equal to this and NM is nothing but my y distance, which is here, and that is this distance nm, I am sorry, yeah, this distance, yeah. So, that is my y distance, I am measuring along the y axis, and so it is y dash cos t divided by sh, and then I can write the values of sh and here h minus. So, I am putting the value of scale only. So, because of the inversion it is coming this one, right, and scale is nothing but same. This is my scale sh, I am putting here also, I am putting here also. Now, I can say that what is the distance here for 2 points. Let us say you measure x, this distance for one point, and y also for one point A. Similarly, you also measure for point B, and then you can find out the length on the ground surface is equal to this distance. That is the idea here. Let us look into the tilt distortion. Okay, because of the tilt distortion, what will happen? My image is appearing like that, not the rectangle one. Fine. So, this is my tilted photograph. So, let us say this is the plane of tilt. Okay. So, this plane of tilt is this which is shown here on the image, planimetric image, right. Now, O is my exposure center and this is another point. So, this is the image of the another point here, okay. K, there is a K point, and this is my tilt angle. Now, let us see there are 2 points A and B on the tilted image, okay. They are appearing like this at the extreme of the image. I am deliberately taking it and we will see why. Okay. So, this is my isocenter I, which is nothing but here. This is my isocenter I here, this point. Okay. If I draw now the vertical photograph, which is should be correct one. So, this is my vertical photograph like this. So, this is the vertical photograph here. So, it is the plane of the vertical photograph indicated by this line. Now, this vertical photograph will have n dash as the, if it is vertical, then this optical axis, sorry, this is my optical axis here, and this is the plumb line from the exposure station, right. So, plumb line is intersecting the vertical photograph at n dash, but it is intersecting at n for the tilted photograph, as you can see here. So, this is my again tilt angle. Now, I am connecting the exposure station with the point A and B on the tilted plane. So, these are the point A dash and B dash, which are the image if we have taken the vertical photograph. In fact, we are trying to derive what is the distortion. That means, if photograph was vertical, I could have got A dash B dash, but now real points are A, B on the tilted photograph, and as a result I want to find out what is the distortion from point A dash and B dash because photograph is tilted. So, let us see. So, this is my A dash and B dash, okay. So, let us see these angles are alpha and beta, right. Once again we look into the animation. So, I want to tilt my tilted photograph such that it will meet with the vertical photograph, and that will give me an idea that if this is point A and it is going to make point A double dash, I already know what is point A dash. So, this point is going to make A double dash. So, this will be my distortion in point A. Similarly, I can find out distortion in point B also on the image. So, let us rotate the tilted plane and make it equal to the vertical plane, match with the vertical plane, or the match the tilted photograph with the vertical photograph like this. So, because of the rotation, what happens is the distance from this point I to B is equal to I to B dash. So, this distance I can write here, A dash A is equal to dA, that is the distortion, tilt distortion in point A. This is this distortion you can see here, and it is equal to the IA dash, I to A dash, right, minus I double dash, A dash, right. This is point is A double dash here, and this is your A dash. Now, I know that IA dash is Similarly, I can write for point B, right. So, B dash B is my distortion in the point B, the tilt distortion, and I can write it IB minus IB dash here. Well, you are agreeing with that? Okay. Yes, here I have written IB dash and IB straight away, right. You will see I can also write here, instead of IB, I can write IB double dash also, the way I have written here. Why? Because of the rotation, this distance IB is equal to IB double dash. We have not projected the point B onto the vertical photograph, rather we have rotated it. So, it is kind of this effect. I can say here, let us click. So, if I have a radius r here, if I rotate by some angle, then it will again here go here, and this point will be go here, and a circular arc. So, this distance is r and it is also r. So, the same thing I am doing here. So, now I can see that if I join these points, different rays, so this is my final connection between the tilted photograph and the, so these lines you can see, they are intersecting also at I, and they are intersecting here as well as here, and so on. So, that is the concept of the tilt distortion. These two amounts are my tilt distortions. Now, let us try to find out mathematically what is the amount of tilt distortion. So, this is my focal length in the tilted plane, and this is also equal to the focal length in the vertical photograph, because I have finding out what is the equivalent vertical photograph of the tilted photograph, right. Now, I can say this is my tilt distortion dA in the photograph, in the animation. So, I can write it like this. I can also write it like this. You can see here that IA dash is equal to this one. Okay. Similarly, we can see here, yeah. Now, IA dash here is equal to N dash A dash, right, and minus N dash I, and I can write it easily F tangent T plus alpha and minus F tangent T by 2. So, that is I determined this quantity. Now, I want to find out this quantity IA. So, IA is nothing but equal to K A plus K I, that means this is K A and plus K I, these two distances shown by the dark color here, and it is equal to F tangent alpha and F tangent T by 2. So, you can use these triangles and find out what is my F here. Okay. Now, I can straight away derive this term here, what is the tilt distortion for point A, which is lying below or above the tilted photograph, you can imagine, right. And similarly, I can write this expression. So, what about point B? Again, this is my focal length F. So, that is my distortion dB. You can see here that because of the tilt distortion, point A is shifting inside like this, but point B is shifting outside, right. So, I can write this thing here, and they are equal basically, right. You know the reasoning, because we have rotated the image, tilted image into the vertical image, right. So, I can write here dB is equal to nothing but IB minus IB dash, and IB dash itself is equal to N dash B dash plus N dash I from this simple relationship of the vertical photograph. Okay. So, now I can see that IB is equal to KB, here I am writing IB here, KB minus KI and equal to F tangent beta minus F tangent T by 2. Now, similarly, I can write that dB is equal to F tangent beta minus this distance, that means I am just doing some algebraic summations here, fine, and where this tangent alpha is nothing but Ka by F. Here this distance, if you see, alpha is Ka divided by F, fine. Similarly, tangent beta is nothing but KB divided by F. So, my KB, I can say here, yeah, KB, this distance, KB divided by F, this is vertical, this is the F distance here, focal length. So, I can find out tangent beta also, tangent alpha also, focal length is known to me, tilt is known to me, I can find out what is the dB or the tilt distortion of point B. So, you can find out for any point, and that is why we have taken 2 points, one is below the photograph and one is above the photograph. That means one is below the vertical photograph, point A, for example, this point B is below the photograph, vertical photograph, and this point A is above the vertical photograph in the tilted plane, and we find out the expression of tilted foot scale. So, let us look into the relief distortion on the tilted photograph. So, this is point A here, this is another point here, A0 I can say, okay. So, let us see this thing A0 here. Now, this thing I am drawing some animations, you can see very carefully, they are very easy to understand, isocenter. So, now this is the situation here, right. And now, that is a R0 distance from isocenter to the B0, that means this is the B0 here and this is the B point and this is the height HB here. Now, this distance is R, and I can see here that this equation is still applicable if I measure the R and R0 from another point N and not the principal point. So, I can write this expression also. So, finally, the radial displacement of a tilted photograph is radial from the another point and not the principal point, that you should remember in case of tilted photograph, and this depends on these factors. As we see in the expression, we have all these involved factors, right, R and R0 here, H small h, let's put the principal line and the, so that is nothing but my x dash and y dash. So, here we finish our this lecture on the vertical photogrammetry, and that is all about the vertical photogrammetry. In the next lecture, we will talk about the stereo photogrammetry, that is the principle of creating 3D from multiple images, not the one images. Today we have seen that we have find out the height from a tilted photograph or from the relief displacement of a one single photograph, and photograph could be vertical photograph or tilted photograph. But tomorrow in the next lecture, we are going to see how can we use two stereoscopic photograph and the concept of stereoscopy to find out the 3D points or the 3D elevation of various points with planimetric position also. So, till then, thank you.